Ammonium perchlorate composite propellant is a modern solid-fuel rocket used in rocket vehicles. It differs from many traditional solid rocket propellants such as black powder or zinc-sulfur, not only in chemical composition and overall performance but also by the nature of how it is processed. APCP is cast into shape, as opposed to powder pressing as with black powder. This provides manufacturing regularity and repeatability, which are necessary requirements for use in the aerospace industry. Uses. Ammonium perchlorate composite propellant is typically used in aerospace propulsion applications, where simplicity and reliability are desired and specific impulses of 180 to 260 seconds are adequate. Because of these performance attributes, APCP is regularly implemented in booster applications such as in the Space Shuttle solid rocket boosters, aircraft ejection seats, and specialty space exploration applications such as NASA's Mars Exploration Rover descent stage retro-rockets. In addition, the high-power rocketry community regularly uses APCP in the form of commercially available propellant reloads, as well as single-use motors. Experienced experimental and amateur rocketeers also often work with APCP, processing the APCP themselves. Composition. Overview. Ammonium perchlorate composite propellant is a composite propellant, meaning that it has both fuel and oxidizer mixed with a rubbery binder, all combined into a homogeneous mixture. The propellant is most often composed of ammonium perchlorate, an elastomer binder such as hydroxyl-terminated polybutadiene or polybutadiene acrylic acid acrylonitrile prepolymer, powdered metal, and various burn rate catalysts. In addition, curing additives induce elastomer binder cross-linking to solidify the propellant before use. The perchlorate serves as the oxidizer, while the binder and aluminum serve as the fuel. Burn rate catalysts determine how quickly the mixture burns. The resulting cured propellant is fairly elastic, which also helps limit fracturing during accumulated damage and high acceleration applications such as hobby or military rocketry. The composition of APCP can vary significantly depending on the application, intended burn characteristics, and constraints such as nozzle thermal limitations or specific impulse. Rough mass proportions tend to be about 70-15/15 SAP/HTPB tal, though fairly high performance, low smoke can have compositions of roughly 80-18/2 SAP/HTPB tal. While metal fuel is not required in APCP, most formulations include at least a few percent as a combustion stabilizer, propellant opacifier, and increase the temperature of the combustion gases. Common species oxidizes ammonium perchlorate as the primary oxidizer, metal oxide catalysts as thermite oxidizers, high-energy fuels aluminium, magnesium, zinc, low-energy fuels acting as binders hydroxyl-terminated polybutadiene, carboxyl-terminated polybutadiene, polybutadiene acrylonitrile. Special considerations. Though increasing the ratio of metal fuel to oxidizer up to the stoichiometric point increases the combustion temperature, the presence of an increasing molar fraction of metal oxides, particularly aluminum oxide precipitating from the gaseous solution, creates globules of solid liquids that slow down the flow velocity as the mean molecular mass of the flow increases. In addition, the chemical composition of the gases change, varying the effective heat capacity of the gas. Because of these phenomena, there exists an optimal non-stoichiometric composition for maximizing ISP of roughly 16% by mass, assuming the combustion reaction goes to completion inside the combustion chamber. The combustion time of the aluminum particles in the hot combustion gas varies depending on aluminum particle size and shape. In small APCP motors with high aluminum content, the residence time of the combustion gases does not allow for full combustion of the aluminum, and thus a substantial fraction of the aluminum is burned outside the combustion chamber, leading to decreased performance. This effect is often mitigated by reducing aluminum particle size, inducing turbulence, and/or by reducing the aluminum content to ensure a combustion environment with a higher net oxidizing potential, ensuring more complete aluminum combustion. Aluminum combustion inside the motor is the rate-limiting pathway, since the liquid aluminum droplets limit the reaction to a heterogeneous globule interface, making the surface area to volume ratio an important factor in determining the combustion residence time and required combustion chamber size, length, particle size. The propellant particle size distribution has a profound impact on APCP rocket motor performance. Smaller AP&Al particles lead to higher combustion efficiency but also lead to increased linear burn rate. The burn rate is heavily dependent on mean AP particle size, as the AP absorbs heat to decompose into a gas before it can oxidize the fuel components. This process may be a rate-limiting step in the overall combustion rate of APCP. The phenomenon can be explained by considering the heat flux-to-mass ratio. As the particle radius increases, the volume increases a cube of the radius. However, the surface area increases as the square of the radius, which is roughly proportional to the heat flux into the particle. Therefore, a particle's rate of temperature rise is maximized when the particle size is minimized. Common APCP formulations call for 30 to 400 micrometers AP particles, as well as 2 to 50 micrometers AL particles. Because of the size discrepancy between the AP and AL, AL will often take an interstitial position in a pseudo-lattice of AP particles. Model: high-power rocketry applications. Commercial APCP rocket engines usually come in the form of reloadable motor systems and fully assembled single-use rocket motors. For RMS, the APCP grains are loaded into the reusable motor casing along with a sequence of insulator discs and O-rings on a nozzle. The motor casing enclosures are typically bought separately from the motor manufacturer and are often precision machined from aluminum. The assembled RMS contains both reusable and disposable components. The major APCP suppliers for hobby use are Aerotech Consumer Aerospace, Animal Motor Works, Chesaroni Technology, Cosden, Loki Research. To achieve different visual effects and flight characteristics, hobby APCP suppliers offer a variety of different characteristic propellant types. These can range from fast burning with little smoke and blue flame to classic white smoke and white flame. In addition, colored formulations are available to display reds, greens, blues, and even black smoke. In medium and high power rocket applications, APCP has largely replaced black powder as a rocket propellant. Compacted black powder slugs become prone to fracture in larger applications, which can result in catastrophic failure in rocket vehicles. APCP's elastic material properties make it less vulnerable to fracture from accidental shock or high acceleration flights. Due to these attributes, widespread adoption of APCP and related propellant types in the hobby has significantly enhanced the safety of rocketry, environmental and other concerns. The exhaust from APCP solid rocket motors contains mostly water, carbon dioxide, hydrogen chloride, and metal oxide. The hydrogen chloride can easily dissociate in water and create corrosive hydrochloric acid. The environmental fate of the hydrogen chloride is not well documented. The hydrochloric acid component of APCP exhaust leads to the condensation of atmospheric moisture in the plume, and this enhances the visible signature of the contrail. This visible signature, among other reasons, led to research in cleaner burning propellants with no visible signatures. Minimum signature propellants contain primarily nitrogen-rich organic molecules and, depending on their oxidizer source, can be hotter burning than APCP composite propellants. Regulation and legality. In the United States, APCP for hobby use is regulated indirectly by two non-government agencies, the National Association of Rocketry and the IEEE Rocketry Association. Both agencies set forth rules regarding the impulse classification of rocket motors and the level of certification required by rocketeers in order to purchase certain impulse motors. The NAR and TRA require motor manufacturers to certify the motors for distribution to vendors and ultimately hobbyists. The vendor is charged with the responsibility to check hobbyists for high-power rocket certification before a sale can be made. The amount of APCP that can be purchased correlates to the impulse classification, and therefore the quantity of APCP purchasable by hobbyists is regulated by the NAR and TRA. The overarching legality concerning the implementation of APCP in rocket motors is outlined in NFPA 1125. Use of APCP outside hobby use is regulated by state and municipal fire codes. On March 16, 2009, it was ruled that APCP is not an explosive and that manufacture and use of APCP no longer requires a license or permit from the ATF.